Hello everybody. Today we are going to discuss about the supramolecular chemistry in surfactants, amphiphiles, and eventually we will talk about supramolecular gelators. So this is quite a wide area of interest, where now we are going to focus on a specific class of molecules which we refer to as amphiphiles. And it is also important to realize that the molecular recognition events now we'll be talking about are mostly in the liquid state. That is, we'll be looking at the assembly of molecules in the liquid state. So the liquid state, unlike the solid state, is also not very much well characterized in terms of the order. That means the order of or arrangement of the molecules is not like that of the solid state, where the molecules are very tightly packed. But what happens in the liquid, the molecules are definitely having some random orientations, and they also tend to have a lot of flexibility in terms of molecular motion. But still, in spite of this flexibility, because of the events of thermal energy associated with the molecules, they are free to move around in different regions of the liquid. But then there also exist hydrogen bonds between specific functional groups of the liquid molecules. So we also have so liquids are also characterized by a certain range of ordering. However, the extent of ordering is much reduced compared to that of the solids. So the liquid state is a disordered collection of molecules that exhibit rapid motion. So this is the first property or attribute of the liquid state. And the thermal energy in isotropic liquids is greater than the strength of the interactions which are relatively smaller in magnitude. So because of this thermal events, because of thermal energy associated with the collection of molecules in the liquid phase, they tend to exhibit a random motion in different regions of the liquid, and this dynamic events is much stronger than the strength of the interaction between the molecules, which is much smaller in magnitude. In spite of the fact that the molecules exhibit rapid motion and the thermal fluctuations in the system are of sufficiently large magnitude, yet overall the cooperative role of intermolecular interactions is still of relevance. The cooperative role of intermolecular interactions between the molecules in the liquid is still of relevance to maintain the condensed liquid phase. Okay, so we cannot ignore overall the role of intermolecular interactions in liquids, and they are also of relevance to maintain the condensed liquid phase. And one such additional significance of the liquid phase is reflected in liquid crystals, which exhibit a certain degree of order in the arrangement of molecules in the bulk phase. Now, that means they do not have the extreme or random like motion associated with pure liquids. They do not have the absolutely frozen geometry which are characteristic of that of solids, but they have but they exist in a phase which is intermediate between that of the solid and the liquid, and this is a special phase which exists, and they are referred to as liquid crystals, and they exhibit very different properties. We will talk about liquid crystals towards the later part of this week, and so the presence of liquid crystals also characterizes the significance of the liquid state. And for example, we can also see that water, because of the extensive hydrogen bonding, exists at P0 1 atmosphere and T equal to 100 degrees centigrade. Whereas in case of hydrogen sulfide, the hydrogen bonds are quite weak. That is, we have got the SHS versus OHO. So the SHS hydrogen bonds are quite weak, and the boiling point is minus 61 degrees centigrade in spite of the high molar mass of H2S. So in principle, when the molecular weight is more, the boiling point should also be higher, but in this case, because of the weak hydrogen bonds involving SHS in case of H2S, that lowers the boiling point to minus 61 degrees centigrade. So this importance of liquid ordering is also of relevance further in liquid ordering is also of relevance in biological cell membranes. For example, we have got bulky phospholipids, okay, and these are actually forced to order themselves in water, and this involves the combination of hydrophobic effects and interactions between the solvent and the hydrophilic polar head. The hydrophilic polar head forming vesicles, that is cells that are vital to life. So the combination of the hydrophobic effects and the interaction between the solvent and the hydrophilic polar head form vesicles that are vital to life. And for example, these are involved, and we have already seen they play a very important role in biochemical transport, cellular signaling, and also protect the sensitive intracellular enzymes. So, you see the relevance of this ordering of the liquid molecules that is of relevance in biological cell membranes as well. And liquid crystals are of relevance in LCDs. Today we know that liquid crystal display technology is very popular and very important, and therefore this is a good application of a liquid ordering, that is the formation of the liquid crystals. So, keeping this background in mind, now let us go to very specific arrangements, supramolecular arrangements of molecules that contain hydrophobic plus hydrophilic sections. Okay. So, we can look at now surfactants, for example, to start with. And in case of surfactants, it is a molecule that has got two distinct zones. That is, it has got a polar head which can be negatively charged or positively charged, or it can be having both negative and positive charges, that is heterodionic, and it has got a non-polar hydrophobic tail which is also a part of the surfactant. So, there are two distinct zones and they both exhibit different solubilities. So, the hydrophilic zone is water soluble and the hydrophobic zone or the lipophilic zone, this is soluble in organic solvents. And because of this dual behavior, they are referred to as amphiphites. They are referred to as amphiphites. Now, let us take some specific examples of these amphiphiles. For example, we can first take a very classic example, a very popular example of sodium dodecyl sulfate, SDS. And let us look at this structure. Okay, so we have got 12 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, we have got this the hydrophobic part and this is the hydrophilic part, or the one which interacts with the water molecules. Similarly, we can also have the phosphatidylcholine. The phosphatidylcholine is and we have so we have this chain here and we have again so we again have this chain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, we have this phosphatidyl chain and again this is the lipophilic part and this is the This is the hydrophilic part, and in this case these can be aliphatic hydrocarbons, fluorocarbons, aryl rings, or other non-planar I mean to say non-polar groups. Whereas the polar part here can be sulfonate, phosphate, carboxylate, ammonium, etc. So these are the polar groups, and based on the presence of the different hydrophilic and the lipophilic parts, that is based on the functionality, there are 4 classes of surfactants. Number 1, anionic surfactants like phospholipids and soaps. Number 2, cationic, that is quaternary ammonium salts. Amphoteric, that is butyenes, which are deuterionic in nature. And let us take one particular example, C19 H38 N2O3 CH3 NH So we have both the positive charges and negative charges in the same molecule, and finally we have got the non-ionic fatty acids. So we have these kind of species and these 4 classes of surfactants, and now we would like to see how we actually investigate the interaction of these large chain like molecules with the aqueous phase. So now we would like to see that you have now got the amphiphile and you have first dissolved it in organic solvent in which the amphiphile is soluble, and then you carefully poured this onto the surface of an aqueous medium. So you have an amphiphile, you have an organic solvent, you mix these two and then you pour this onto the surface of an aqueous medium. The organic solvent is then evaporating and the amphiphiles are then packed into a condensed monolayer. So what happens is that when you pour this mixture of the organic solvent and the amphiphile, in which the amphiphile is soluble, onto the surface of, say for example, an aqueous phase, for example water, the organic solvent starts evaporating and these hydrocarbon molecules or amphiphiles now start coming close to each other to eventually form a monolayer. This is what leads to the formation of a monolayer, and the thickness of this monolayer is 1 molecule thick. So now let us see how this particular process is achieved. So we have a trough, okay, and here we have put a movable barrier, okay, and here we have got, so this is the movable barrier, this is the aqueous phase, and on this you have poured the amphiphile plus the organic solvent. So now you see that the polar part is in contact with the water molecules, and the non-polar part is actually now exposed to the air interface. So, at the interface of air and water, these the hydrophobic part is now exposed to air, whereas the hydrophilic part is in contact with the water molecules, and we can now form this monolayer, another layer at the back. So, in this way you see that the molecules are now getting tightly packed, and as you increase this movable barrier, so you have this monolayer, and as you now move this barrier, now the area which is available to the molecules is decreasing, and now the molecules come closer to each other and they form this tightly packed monolayer on the surface of the water molecules. And the pressure which is created can be measured. Pressure can be measured using a pressure sensor, that is, the lateral pressure can be measured using a pressure sensor. So, now we see that the surface tension of clean water at room temperature is 72 millinewton meter inverse. Now, what do the amphiphiles do? The polar part of the amphiphiles actually form strong hydrogen bonds with the water molecules, but now the non-polar parts actually they are actually in air, and there are very weak interactions between these non-polar parts. Because of weak interactions between the non-polar parts, it reduces now the surface tension. So, there is a drop in the surface tension, and it also decreases the pressure which is now present, and this change in the pressure can be now quantified as gamma pure water minus gamma surfactant, which gives you the lateral pressure. It is also important to characterize that when you are slowly moving the barrier and decreasing the surface area available to the molecules, then you have the formation of the monolayer. It is a tightly packed layer. As the molecules come closer to each other, there are different thermodynamic processes here which takes place. So, initially the molecules are free to move at the interface, but then the decrease of the available surface area makes them come close to each other, and there exists ordering of the non-polar parts of these hydrophobic molecules, and we can now monitor the pressure pi as a function of the surface area of each molecule, and this gives rise to this kind of a curve, and this kink characterizes a second order phase transition, and a finite discontinuity characterizes a first order phase transition, and this is the coexistence region. So, you can now see very clearly that as a function of pressure and surface area of each molecule, what are the thermodynamics associated with the processes that favor chain ordering in the liquid state, which characterizes these surfactant like molecules when they order in a specific way at the water air interface. So, now this process is very important, and this is the process which actually is also the basis of the mode of action of soaps, which is able to remove the organic oils in water. Because when you put this soap, then what happens is that the polar parts actually stick to the water molecules, the non-polar parts stick to the oil, and now when you wash it off, then the surfactant, when it is getting removed, then the dirt is also being removed by sticking to the hydrophobic part, and this is the mechanism or the mode of action of soap like action when you put these surfactants in water. And these are also responsible for spreading, wetting of surfaces, including dispersion and formation of emulsions. Including frothing. And the way in which these surfactant structures organize themselves in the liquid state can also change. They can exist in different kind of ordered structures. So, the different ordered surfactant structures are, we can have a bilayer, so this is a bilayer, so we can have a bilayer, we can have a monolayer, this is a monolayer, overall this is a bilayer, we can have a micelle formation, where we can have the polar heads which are actually solvated by water, and we can also have the reverse micelle, you can also have the reverse micelle when you dissolve the surfactant in a non-polar solvent. Then the non-polar parts or the lipophilic parts are actually stabilized by solvation with the solvation by the non-polar solvent. And we can also have the formation of vesicles, where you can now have so these are all my polar heads, and in between I will have the non-polar parts. Okay, so you can see here now this is a polar part, this is a polar part, in between we have got the non-polar part. So this forms a spherical arrangement which we call as vesicles. So these kind of nice array of ordered surfactant structures can form when we actually dissolve surfactant molecules in water or in a non-polar solvent. They can either form these bilayers or they can form micelles, or they can form reverse micelles as well. So in the next lecture we will now be looking at the phase diagram of these micelle like structures, and look into further investigations of these assemblies which are existing at the interface of air and water. Thank you.